Hello everyone and welcome back to another video. Today we'll be taking a look at a British Informatics Olympiad question, and we'll be taking a look at the 2022 paper and the second question from it. Let's have a quick look at the question first. Okay, so I've basically highlighted in yellow what's important, so feel free to pause the video and have a read if you haven't already seen this question before. And now I'll quickly go onto the whiteboard and explain what the high-level solution for this question is going to be. Okay, so first of all, before we start this question, this is one of the harder questions out of the question two. So, if you feel like you're not understanding it, don't worry. It's a very difficult problem. But now with that said, let's just get into the actual solution for it. So one key part of this question is finding out a suitable way to represent each of these numbers. Since representing them as their numerical numbers 1, 2, 3, 4, 5 poses significant problems. Like one of them, for example, is that if we have 8, for example, versus 5, the neighbors of 8 are going to be these numbers. And then we can't generalize it, saying that the neighbors of 8 are, its top left neighbor will be -5, its top right neighbor will be -4, since that's basically different for 8 compared to 5, and that will be different for 12. It will basically be a bit of a pain if we try and represent all of its neighbors relative to its current position. For example, if we consider 8 and 3, so the top left position to 8, that's -5 of whatever its current value is. But the top left position from 12, that's going to be 6, so it's going to be -6 of whatever its value is. So it's basically different, and this will pose significant challenges if we try and do it this way. So if that's not a suitable way to represent this hexagonal grid, then what will be? One of the ways which we could do this, which is suitable, is representing each of them in a Cartesian format, basically. So if we consider these to be the columns, this is column 0, column 1, all the way, and then this is column 5, column 4, finally. And then this is row 1, or row 0, sorry, then row 1, then row 2, 3, and then finally row 4, over here. Okay, so that basically means that this is represented using the coordinate 0, 0. This would be represented using the coordinate 0, 1, etc., etc. So if we take this arbitrary number, 14, so it's basically on the second row, it's on this row, and then it's on the 0th, 1st, 2nd, 3rd column. So its coordinates would be 2, 3. This basically provides us a much easier way to represent each of the numbers. And the reason why this will be significantly easier is basically because of this reason. So what we need to do in the problem is we need to, given we're on a certain square, we need to transition to another square. So let's say from 15, if we need to transition to 24, if we have a modifier of 9, then what the problem allows us to do, what this representation allows us to do, is identify the neighbors really easily. Because for 15, its coordinates are basically going to be 2, 4, which means that its neighbors are going to have coordinates 2, 3, and then since 2, 3 will be the one on the left of it, so that will be 14, then it will be 2, 5, that will be the one on the right of 15. And now you might be looking at the grid and and saying to yourself that, well, 5 isn't actually on the grid, so how can 2, 5 be a valid coordinate? Exactly, it's not a valid pair of coordinates. However, this is the neighbor, which is on the right of it. So if we encounter a row column value which is outside of the range 0 to 4, we know that that's not valid. So this is basically the left neighbor, this is the right neighbor, and then the neighbor on the top left is basically going to have coordinates 1, 3, subtracting 1 from each of the xy coordinates. The neighbor on the top right will have coordinates 2, 4, which is adding 1 to the y coordinates, keeping the x coordinate, keeping the y coordinate the same. And then likewise for the bottom ones, like I'm sure you can just extrapolate the relationship we drew over here and figure out what it is for the bottom ones. However, one small catch is that similar to the number problem and number representation, we also have a slight problem with the coordinate representation, is that the neighbors of 14 or 15 are basically going to be different to the ones of 7. Since 7's basically on an 7's basically on an odd row, So let me just write this down. So this is on odd row, but this is on even row. So 7's neighbors will basically we'll need to come up with a different set of rules to find out what 7's neighbors are. And we'll be going through these rules in just a second when we actually look at the code line by line. But that's pretty much the representation of it. But we haven't even got to the two main functions which they want us to actually perform, which are the skirmish and the feud. So if we first look at the skirmish, since that's by far the easier one, how we basically represent the skirmish is basically we start at a certain coordinates, and then we basically increment our position by n, where n is the modifier for that particular color. And then we go to the, let's say n is 9, and we start at 3. So then we go to the 12th position. And then we basically check all the directions. So what the direction does is it checks whether this particular edge is already fulfilled, this edge is fulfilled, this edge is fulfilled, etc. And now here's where I'll also mention, the problem is basically a group of edges which are between the nodes, right? So let's just consider this edge. So one of the edges in the problem would be the edge between 1 and 6. So we can represent that edge as being two coordinates, which are 1 and 6. But then we're not going to represent 1 and 6 using their numerical values. We're instead going to represent them with their coordinate values. So it'd be the coordinates of 1 followed by the coordinates of 6. So 0, 0, followed by 1, 0. And this over here is basically how we're going to represent the edge which connects 1 and 6. We're going to have the coordinates of the first one as well as the coordinates of the second one. And now if we want to represent this particular coordinates, the one between 3 and 4, then we basically have the coordinates of 3, which are 0, 2, followed by the coordinates of 4, which are 0, 3. Okay? So that's how we represent the edge between two particular hexagons. Okay? And now back to our discussion which we were having on the feud, on the skirmish, sorry, how exactly we carry out the skirmish. So the way we do this is after we increment the modifier position, and then we land in a position, let's say 12, then we need to basically check all 6 of its directions. These directions go from 1 to 6, exactly how the question had it, 1 to 6 being like this. And then we check whether this particular edge is already there, but whether the edge connecting 12 to 6 is there, the edge connecting 12 to 7 is there. If none of these edges, if a certain edge is not present, then we know that that edge is basically free, so we can that can be our value for the edge which we append on that particular move. So that's basically how we're going to append the edges. And now let's discuss how we're going to implement the algorithm for deciding the feud. Okay, so how we determine the feud is basically whichever preferred edge there is. So what we do is we basically iterate through every single hexagon as well as every single edge within those hexagons. And then we basically we create a copy of whatever positions there currently are. So let's say that this is the current positions array. We create a copy of this, which is the new positions array. And now this new positions array, what we do is then we append this particular position which we're adding, which we're currently exploring. And then after we explore that position, we then count the number of points which red would have and blue would have. And then we can basically determine whether red has gained control of any hexagons or lost control of any hexagons. And then that will basically determine whether that particular edge is good for red or not. Okay, so this might seem a bit like wishy-washy without looking at the code. So let's have a quick look at the code first. First, I'll just go through these 3 main structures which we have here. So you basically have boost. So boost is basically just a modifier which we add to the positions of each of red and blue. And then we basically have current position. So this current position basically stores the starting positions of each of red and blue, but then this will get updated as the game progresses. And then we have hive. So this hive basically stores every single hexagon as well as every single edge within those hexagons. So now one thing worth mentioning is that we also need to keep track of which colored B is within each edge. So 2 corresponds to a color of no one, and then 1 corresponds to a color of blue, and 0 corresponds to a color of red. Okay, so now let's go through the skirmish function. So actually, before we go through the skirmish function, it's probably more suitable to go through the get neighbor function. So what this does is, given a certain number, given a certain number and given a certain direction, we can get whichever neighbor is present. So for example, if we go back to the question, if we consider like the hexagon 13, and then if we consider direction 1 from hexagon 13, then the neighbor from direction 1 of 13 is going to be 8, okay? And then similarly, the direction 3 neighbor of 13 would be 18. So we basically need some sort of function which decides which neighbor is going to be present. So first, we basically convert the num into its row and column values. And then remember, the row value is basically going to be whatever the number is subtracted by 1, and then its quotient when divided by 5. That will be the row value. And then its column value will be number minus 1, and its remainder when divided by 5. And this is basically how we translated between the numerical and the coordinate systems, which we went through a few minutes ago. Okay, so that's how we determine the coordinates of the particular number. And now we basically have two separate situations here. First of all, if the direction is basically 0, if the direction is 1 or 6, which means it's pointing this way or that way, then the new row will be row minus 1, so whatever the current row is, minus 1. And then if the direction is 2 or 5, then the new row will be the same row as the current row. Otherwise, the new row will be one higher than the current row. But now, determining whatever the column value, this varies depending on which row you are. So remember, as we talked about earlier, if the row value is even, then it will be different to whether the row value is odd. So let's consider the row value being even first. If the row value is even, then basically if the direction is 6, 5, or 4, which means 6, 5, or 4, if it's one of these, then the new column will be column minus 1. Otherwise, if the direction is 1 or 3, then the column will be column. Otherwise, it will be column plus 1. Okay, so I won't go through exactly each of these conditions, since the video will be like 3 hours long if I do. But then just like feel free to actually just to take up like a situation. So for example, consider an element like 12 or something, which is on an even row, and then just consider its direction neighbors, and then consider which columns they are in, and then this function will make perfect sense. And then likewise, if the row is basically odd, then we have a different set of rules deciding for whatever the new column value is, given the certain directions. So if the direction is 6 or 4, then the new column value will be the same. Otherwise, it will be 1 minus, otherwise it will be 1 plus. So these are basically all the different conditions which we have. And now, after we do this, we basically just need to determine what the new direction is. Okay, so what this new direction basically means is, since the direction connecting one hexagon to its neighbor will be different to the direction connecting that neighbor back to the hexagon, right? It'll basically be the reverse of it. If we go back to the question, this becomes very clear. Basically, if we consider hexagon 7 and 13, then the edge connecting 7 to 13, that's basically along direction 3. However, the edge connecting 13 to 7, that's direction 6. Okay? So the new direction is basically the direction from the new neighbor to the original node, which we are currently at. So if the direction is 4, 5, or 6, then the new direction is direction minus 3. Otherwise, it's direction plus 3. Okay? So a direction of 1 would correspond to 4, 4 corresponds to 1, 2, 5, 5, 2, 3, 6, 6, 3. And then finally, we return the coordinates of the new row and column, as well as the new direction. So that was the getNeighbor function. And now we basically leverage this getNeighbor function within the skirmish function. So what the skirmish function does is we basically start by getting whatever the current position is of the particular color which we're going through, and then as well as whatever the current direction is. So both these are just things which are stored within the current position. Since the current position, first thing which it stores is the number, second thing which it stores is the direction. So that's the current position, the current direction. Now the new position will be the current position plus boost of the color, but then mod 25. Since basically if it goes beyond 25, then we need to subtract off 25. So that's why it's mod 25. Okay. So now one more thing after this is we basically need to update the current position and the current direction. We need to update that particular edge with having the new color. However, one important thing is we also need to update the edge of the neighbor of that particular hexagon. So for that, we need to get the neighbor, which we leverage the getNeighbor function from. We get the coordinates of the neighbor. And now, if the coordinates are within the bounds, this is very important, since if the coordinates were 0, 5, for example, for 5's neighbor, as if the coordinates were 0, 5, then we know that there's nothing to the right of it. So only if there's something to the right of it, then what we do is we basically set the new num to equaling 5 times the new row plus the new column plus 1. This basically gets the new neighbor. And then we basically set the hive, we basically update the edge of the new neighbor to be in the color as well. And now if the color is basically 0, i.e. if it's a red player, then we basically rotate clockwise, otherwise we rotate anti-clockwise. That's basically the new direction. And then we basically perform the jump. So we basically set the new current position to equaling new pause and then new direction. Then we perform the jump when we next go through the next skirmish for this particular function. Okay, so that's basically it. This is just a debugging message. We can get rid of it. So that's basically it for this particular skirmish function. Okay, so yeah, this was pretty heavy, but the Feud will be much harder. So let's just go through the Feud function. But before we go through that, we need to go through the getOwner function. So this getOwner function will be fundamental in going through the Feud function. What this getOwner function does is this basically gets it tells us which colony controls a certain hexagon. So it returns the owner of a certain hexagon colony. So we first need to determine what the count of red and the count of blues are within that particular element. And then if the count of reds is greater than the count of blues, then it's controlled by red, since the color 0 corresponds to red. Otherwise, it returns 1, since the number 1 corresponds to it being controlled by the blue color. Otherwise, we return 2. Now, 2 basically means it's controlled by nobody. So that means the count of R is equal to the count of B, which means it's controlled by nobody, so we return 2. Okay, and now we basically have the Feud function. So one key part of the Feud function is determining what the optimal edge is. So for that, we have maxi. This maxi is basically whatever the maximum optimal hexagon is, as well as the optimal direction of that hexagon is. And now over here for maxi, we have 6 different key positions, 6 different key elements which we have to store as part of maxi. So these 6 are basically, the first 4 are the directions, first 4 are the criteria for deciding whether to choose that particular element or not. So respectively, they are basically, they are the number of new hexagons you gain control of, then the number of hexagons the other player loses control of, then it's the basically direction, and then it's whatever the hexagon number is. So those 4 are the first 4. We've initialized them all to negative values, since they're basically null values. And then finally, the 2 final ones are basically whatever neighboring position that edge affects. So that basically means that, let's say we add an edge, then we need to know which neighboring edge we need to also change as a result of changing that particular edge. So then what we do is we basically iterate, as we said earlier, we iterate through every single hexagon and every single direction, and then we apply this algorithm. This basically determines whether that particular, how good making that particular edge, taking control of that particular edge will be. Okay, so this is the main heart of this function. It has 2 main parts. The first part is basically if it has a neighbor. So this basically means that we call the getNeighbor function, and then if the neighbor is basically present, then we basically perform this particular part of the code. Otherwise, we perform this part. So let's look at if the neighbor is present. So the neighbor is present if and only if the new row and new column values are between 0 and 4. So then what we do is we basically set the new hexagon value to equaling whatever the 5 times the new row is, plus the new column, plus 1. This was discussed earlier since converting between the coordinates of the numerical representations. And then what we do is we basically set the old status array. So this old status is whatever the old status of the two hexagons were. The two hexagons being the two hexagons which are currently on that edge. And then the new status is basically we first take a copy of whatever the old status is. We take a deep copy of this. And then what we do is we basically need to update whatever the direction of that, whatever direction of the first hexagon we have is, to equaling the color. And then as well as the new status, the new hexagon, we need to update the new direction vector of that as well. We need to set both of these to color. And then what we do is we basically get owner of all of these vectors. So we basically get the owners of whatever the hexagons were before this edge has been updated, and then we get the new owners. And now the hexagons gain control of is basically the new owners, like the count of the color in the new owners, minus the count of the color in the old owners, okay? And the hexagons the other color lost is the count of the colors in the new owners, minus the count of the colors in the old owners. So that's how we determine hexagons gain control of versus hexagons lost. And now, if that particular edge has no neighbors, then we go through these 9 conditions. So this bit of code is exactly the same, just getting the old and new status and the old and new owns. And then we basically have these 9 conditions. So these conditions are very logical. Like if you basically just write them down and think about them, then it will make complete sense. But I'll go through the first one, and then I'll leave you to go through the next ones. So basically, if the previous owner of the hexagon was the color we're currently iterating over, and the new owner is also the color, then no hexagons have been gained control of. Additionally, no hexagons have been lost. However, if the new owner is 1 minus color, this is basically an invalid state, but then just for completion I have it. If we've somehow, after appending, introducing one more color, if the new owner is the opposing color, then we basically gain control of -1 hexagons, and the other color has lost -1 hexagons, since the other color has also gained 1 hexagon. And now otherwise, if the old owner was color and the new owner is nobody, then we basically gain control of -1 hexagons and we lost 0 hexagons. Now similarly, we have all of these conditions. Like for example, if the old owner was the other color, but the new owner is this color, then we've gained control of 1 hexagon, we've the other color's lost 1 hexagon. And similarly, we have the rest. Like this part of the code, it isn't too important if you don't understand it. Like if you understand everything else, then that's much more important than understanding this part. But this part basically just tells us, after implementing that edge, what will the new status of the number of hexagons gain control and lost will be, okay? And now we also set new hexagon in new direction to being -1 and -1. Since in this particular code, in this particular if block, there was no new hexagon, since there was no neighboring hexagon, since the hexagon was basically out of bounds, okay? So that's this main function done, which determines the new hexagon and it basically determines the number of hexagons gained control and lost control of. And then what we do is if the number of hexagons gained control of is greater than maxi 0, so maxi 0 is the best current configuration which we have. If the hexagons gained control of is greater than whatever the best we currently have is, then we update the new maxi to equaling this particular hexagon and direction combination. And now if the hexagons gained control of is equal to maxi, but then if the hexagons the other color lost is greater than maxi, then we basically set the new maxi to equaling this particular set as well. And now, now one more condition is if both the hexagons gain control of and the hexagons lost are the same, but then if the color is basically if the direction and hexagon number is greater, then remember, if the color is blue, then that's preferable, therefore we update it. However, if the color is red, then a later hexagon which we're iterating over will never be preferable, hence we don't update maxi. So that's pretty much how we update the maxi function, maxi variable, sorry. And now that's basically it. And now the rest of the code is just trivial. We basically just need to update whatever the color is of maxi. And then finally, if there is a neighbor of maxi, then we also need to update that particular edge. After updating both of these edges, the feud is basically finished. Okay, so that's basically all four of these main functions done. Finally, we just have this output control. So this basically just outputs the number of hexagons each color controls. And that's pretty much it for this particular code. We finally just need to take in these numbers as input, call them in their respective functions. That's it. Okay, so this was definitely quite a tricky problem. I would highly recommend, if you don't understand a single part, just to change a few things within the code, which you can access through my GitHub, and then just play around for it. You'll definitely get a much better idea of how exactly the code works. If you see like how what the impact would be if those lines weren't there. Okay, so and now let's get on to actually testing this code. Okay. Let's open up the mux scheme. Okay. Let's test on the final three particular test cases. Oh, sorry, I'm running the wrong code. Okay, so this basically outputs 5.3. Program basically outputs 5.3, which is indeed correct. And now let's go on to test the next test case. Okay, now we go here. And then we get 9.2 as the answer. 9.2 is indeed correct. And now we go back and finally we'll test on one more, and then we'll call it a day for this video. And our answer is 7.7, which you can see is also correct. So our program is indeed fully correct. Okay, so that's pretty much it with this particular video. I really hope you enjoyed watching. This was a really intense video, so if you understood the entire thing, then good job, kudos to you. And I hope to see you in another video next time. Thank you very much for watching. Bye.